You're looking at my Excel spreadsheet that I use to make all my calculations with. The left side of the spreadsheet is basically the same as the data table that you had in your lab that you filled out. So you can see here, my first part of the table is for the spinning turntable by itself. And I enter the circumference here and calculate the radius, the circumference divided by 2 pi. All the bold fields are fields that I enter from the data into the data table that I took data in the lab. And I entered my tangential accelerations, which of course came from the slopes of the log-pro graphs. And then all the rest of the table, I use Excel formulas to calculate all these values. So you can see I've done it here for the table by itself, the large brown tile square, the silver metal tile, the wooden cylinder, and the round cinder block, which I call the flagstone. Then once I have the graphs, I have Excel make the graphs, then I can use Excel to find equations of the best fit lines, and that's what you see here. And so I take the slope of each of those lines and I enter them into my table. This is like the table that is at the very bottom of your data table sheet. And once I enter those slopes, which is the inertias of the spinning table plus the objects, then I subtract out, here you can see in my equation, I'm subtracting out the inertia of the table alone to get my experimental value of the inertia of the object. And then compare that to the theoretical value, which is calculated using the formula in table 10-2. And then this is the formula that calculates the percent error. So just now you know what the spreadsheet does. I'm going to be using this to show you the error analysis. When things change, I'll be able to very quickly see how it affects my end results. In this example, we'll take a look at our tangential acceleration values. So here's the table of data for the table by itself. And we had 4 hanging weights, or 4 hanging masses, 50, 90, 130, and 170, and those produce these tangential accelerations. How did we get those tangential accelerations? Well, here's an example. This is run number 3 with the 130 grams hanging on the table by itself. And here's the region of the graph that shows the acceleration of the table, right? My slope of velocity versus time. If you look closely, you can see the line has a little bit of wiggle to it. So that's why we use a best fit line, to take that wiggle and that variation, to minimize that variation. So here is the range of data that I chose, and that gave me a slope of 2.243. If you had chosen a very narrow range, it would be very possible to get something very different than that. Here's an example. Here you can see I've only chosen this narrow range, and you can see because of the wiggly shape of that graph, I am not effectively removing the wiggle with my best fit line because the range is so small. And you can see here that comes out with a slope of 2.6. So if I go back to my data table here, and all I'm going to do is replace this one value of tangential acceleration with 2.6, that will change this data point right here in my graph. This is my torque versus alpha line for the table alone. And you see the slope is 0.0096. And down here, that's what I've got as my value for the inertia of the table alone, 0.0096. And these are my calculated percent errors. And I've copied those numbers here in this second column for comparison. So now when I change this number here to 2.6, there we go, and hit enter, boom, you can see the effect it had here on my graph, and it changed the slope of my graph here to 0.0082. So I'm going to go over here and change now my table's inertia to 0.0082, And look at the difference it makes. Before, my error was 7.5 for the large brown tile square. Now it's 11.8. And you can see this one is huge. The wooden cylinder went up to 23.7 from 4.7 just from that one data point changing. So it can have a big effect. Here we'll look at the effects of having your object not being centered on the turntable. So here is the brick on the turntable, as centered as best as I could center it. It doesn't look very centered from this camera angle, but it is pretty well centered. And then I placed directly underneath the brick a cutout of a white piece of paper to show where the brick was. So now I've moved the brick off center, and you can see the white piece of paper on the turntable shows where the brick was previously. So now let's take a look. Let's enter our data into the Excel file and see how big a difference this makes. Note this brick experiment was done later than all my other experiments, and so it was on a different turntable. So you'll see my value for the inertia of the turntable is different than before. And that's just because I used a different turntable. So this turntable's inertia is 0.0075 all by itself. And then with the brick centered, I got a slope of 0.172. That's this graph with the circles centered. And then when it wasn't centered, I got my new value of slope 0.0191. And so when I plug those values into the data table, wow, what a big difference. You can see here my percent error went from 4.6%, where I thought it was pretty well centered, to just being off center by what I would consider to be very possibly done in the lab. Let's look at that picture again. That is not a whole lot of difference. When we measured the dimensions of our objects that we placed on top of the turntable, those numbers were only used in our theoretical calculations. So if we make mistakes in those measurements, they will only show up here, not anywhere in our graph. So what I've done here for the large brown tile square, it measured 34 by 34 centimeters. I changed that to 33.8. And the silver metal tile, 26.7, I changed to 26.5. So I shortened the sides by 2 millimeters. And you can see what happened. The error went up from 7.8 to 9.1 for the brown tile, and from 6 to 7.6 for the silver tile. Let's try what would happen to the silver tiles numbers if instead of 2 millimeters less, I chose 2 millimeters extra. So I'm going to change this to 0.269. And now when I look over here, I see that the moment of inertia of the silver metal tile, our theoretical value went up. And since our experimental value was above our theoretical, by raising the theoretical, it got closer to that value. And so my error actually went down. So just because I have an increase in my error over here doesn't mean it's going to always give me an increase in my percent error. Another common number that I saw on students' reports was they used 15 centimeters for the radius of the round cinder block. I chose to use the circumference method. I measured the circumference of the cinder block to be 96.5 centimeters. So when I divide that 2 pi, I get this 15.35 centimeters approximately. And a lot of people use 0.15. And so you can see with the circumference method, I got 4.2%. But if you just use 0.15, you got 9.2%. In the data table, there was a place to record the circumference of the table and the radius of the table. So some people chose to measure just the radius of the table. and then calculated the circumference, but that wasn't the point. The point was to measure the circumference and then use 2 pi times the radius to solve for the radius. And why do we choose to do it that way? Well, if you look here, this is how you would measure the radius itself. You can see the challenge is trying to get the 0 point at exactly the center of the wheel. And you can see the millimeter markings on the ruler. You know, it'd be very possible to be off by a millimeter or two to find the exact center of the turntable. So it's much easier to take a string and wrap it around the circumference of the turntable, find its circumference, and then divide that by 2 pi to get your radius. So that's what I've done here. I measured their circumference to be 0.945 meters, or 94.5 centimeters, and from that I calculate the radius is 15 centimeters. So let's see how much of an effect. Here I've calculated, instead of 15 centimeters, 15.2 centimeters for the radius. My error changed for the tile square from 7.8 to 10.6, and you can see all the changes here. It looks like some of them are a little more than 5% change, with a 2 millimeter change in the radius measure. Whereas over here, if I measured the circumference to be 94.5 centimeters, now again I have a difference of 2 millimeters, 94.7 centimeters now, and you can see the difference that makes. The percent errors don't change as much. So this is kind of like the example I used where you measure someone's height and you're off by a foot versus measuring the height of a tall building and you're off by a foot. Your amount of difference, 2 millimeters out of 947 millimeters, where here it's 2 millimeters out of 152 millimeters. So it's a much less percentage over here. And that's what we see. The effect on the error is much less when I have a 2 millimeter mistake out of 947 millimeters versus a 2 millimeter mistake out of 152 millimeters. Let's look now at conversion errors and rounding error. So here is my table for the brick, and I've put here for comparison these same numbers so that when I change something, you can compare what it was before. So I saw one lab group, they here in the dimensions of the brick, here you can see that my measured dimensions is 20 centimeters by 9.4 centimeters. So they measured 10 centimeters instead of 9.4, but they accidentally call that 0.01 instead of 0.10. So let's see what happens if I change this dimension of the brick to 0.01. And as you can expect, the percent error goes kind of through the roof here because that's way off. They're saying the brick is 20 centimeters by 1 centimeter. Oh, so that's a big source of error. If you get big error like that, it's a good indication that you've made a serious mistake, like that one. In the instructions for the procedure, I emphasized in class how important this step number 6 was, that you had to make sure you had the settings set for the ultra pulley to be 10 spoke in groove. What would have happened if you failed to do that? Well, here is the run number 3 for the 130 grams on the turntable by itself. If I go to the settings for the interface, there's my photo gate, and there's the setting that we were supposed to have. If you forgot to do that and you let the default of this other piece of equipment called vernier picket fence stay there, watch what happens to the slope of the graph. Right now it's 2.243, and if I change the setting to that picket fence, now this says 2.243 because that's what I typed, but here's the new slope of the graph using that setting, 7.47 meters per second squared, 3 times as much. So it's a huge mistake, and your data would be completely off if you had this setting. So let's consider now some of the common responses students gave for reasons why our percent error was there. A lot of kids said we neglected to include the mass of the string. So let's analyze what would happen if we did take the mass of the string into account. So here at the beginning, we have quite a bit of string around the outside edge of the turntable. We know that mass at the outside edge of a rotating object, that's where it can have the most effect on the object's inertia. And over here, the hanging mass is not very much string is contributing to the weight that is pulling on the turntable. But as we release it and let it go, more of the string will be here and less of the string will be around the outside edge of the table. So if the mass of the string did make a difference, we would see the inertia of the table decreasing while at the same time the force that is pulling and accelerating the turntable increasing. So that would show up as an increase in the slope of our velocity time graph, right? We would have a lower slope here and a greater slope here to indicate that the acceleration is increasing. So let's go ahead and find, first we'll go to the top 1/3 and take note of the acceleration, about 2.23 meters per second squared. And now let's look at the bottom third instead, 2.27. So it's actually steeper at the bottom than it was at the top. Not by very much, but a little bit. Certainly it's not less like we would expect it to be if the mass of the string made a difference. So I think we can say that the mass of the string is imperceptible. The effects that the mass of the string have on our system are imperceptible. Another common response for the reason for percent error is we forgot to include the inertia of the pulley. If we don't include the inertia of the pulley, what that is saying is that the tension in the string here is the same as the tension in the string here. But if we include the inertia of the pulley, that means this T2 is going to be just a tiny bit less than T1. And T2, of course, is the tension that is producing the torque on the turntable. So if we use the value of T1 instead of T2, we are going to get a slightly different value for the torque. So let's analyze this situation here. I have chosen the direction of motion of the falling mass to be the positive direction. So to agree with that, that means my pulley now, the clockwise direction is the positive direction, and the counterclockwise direction is the negative direction. So T1 times the radius is my positive torque produced by T1. T2 times the radius is my negative torque produced by T2, and the sum of those is my net torque. And of course, that equals I alpha. Alpha, we know, is tangential acceleration divided by radius. So I'm going to make that substitution. And this R here is cross-multiplied down to the denominator to make this R squared. The moment of inertia of the pulley, I went to the Vernier website and I found out information about the pulley. I found out its circumference. So from that, I was able to calculate its radius by dividing by 2 pi. And also, they tell me the value, a numerical value, for the moment of inertia of the pulley. You can see here 1.16 times 10 to the minus 6 kilogram meters squared. So I can solve this equation now for T2, the new tension of T2, and you can see it is less than T1 by this amount right here. Now I'm able to know that the torque from the string on the turntable by force T2, it's T2 times the moment arm, or the radius of the table. So I'm going to go to my spreadsheet again, and in this graph, when I plotted torque versus alpha, you can see for the table alone, here we go. There's my Y data. I'm using the torque from the string that I used, all along. But if I do the new calculation now and figure out the new torque from tension T2, right? This torque right here, these are my new values. So you can see 0.067 became 0.0662. 0.110 became 0.1099. Yes, they are a little bit less. How much effect does that have, though? Let's go here and make a new graph. So you can see here my Y values for this new graph now are right here, those new values of torque from the string. And so when I use those, here is my new graph, and the slope 0.0095. No different, at least to that many decimal places, for the slope of the line and the inertia of the table. Another common response for causes of error was we failed to take into account air resistance. Well, if you think about this falling weight as it falls, it's moving pretty darn slow. So just to be sure, I'm going to create wind that is much greater than the speed of the falling mass. So what I've done is I've hung my 170 grams here from a force sensor. I'm going to record the force over a matter of time, and I'm going to turn this fan on. It has 3 speeds. It'll start off with no wind, and then I'll successively turn it to higher and higher settings, and you will be able to see that the wind is blowing quite readily up against the weight, and we'll see how much it changes the downward force that it exerts. So here we go. I'm recording the force. I've turned on the fan. You can see the little tassels are starting to fly. And I turn the fan to a higher setting until it's full blast. I'm still recording the force over here. And now let's take a look at what that force looks like. Here we go. For the 25 seconds that I recorded it, here at the beginning, the fan wasn't even on. 1.627 newtons. Over here, the fan was going full blast. 1.625 newtons. So barely a difference, if you can even attribute this difference to be because of the wind. And certainly the falling weight did not experience this much wind at any time during its fall. It wasn't going nearly that fast. So I think, once again, we can say this effect has an imperceptible effect on our data. Air resistance is not a factor. Another common response from students about the source of our error was that we failed to take friction into account. There are multiple places where friction exists, so it is important to be explicit and specific about where the friction is. An obvious location of friction is in the rotation of the turntable. This friction was accounted for in our calculations in the pre-lab. Here we see that the net torque equals I alpha. Here we included the torque from friction. We know that the torque from the string is accelerating the turntable, but it's the frictional force that slows it down, so it's in the opposite direction. If we solve this equation for the torque from the string, we get a form of an equation that is y equals mx plus b. And when we look at our graphs, here are the graphs of, if we look at my legend here, the table by itself, and then it goes the wooden cylinder, the silver metal tile, the large brown tile square, and the large cylindrical brick, which I call the flagstone. These are, as we go up the legend, these are in order of increasing weight. So you can see for the lightest objects, the frictional torque is the lowest. And as we go up higher, I'm looking at the y-intercepts here of the equations here. They're increasing until the flagstone has the greatest, 0.0287, has the greatest frictional torque, which makes sense because the heavier object on the turntable will press down on the bearing more, creating slightly more friction. So this agrees pretty well with our method of graphing, and that the y-intercept represents the torque due to the friction. Another location for friction could be in the axle of the pulley. In our analysis of the pulley's inertia, the differences in the tensions on either side of the pulley really were due to both the pulley's inertia and the frictional forces in the pulley's axle. We saw how negligible the effects of that were, so we can effectively ignore the minuscule frictional forces in the axle of the pulley. In conclusion, we can safely say that the main reasons for larger errors in our experiment were factors that were somewhat under our control, such as dimensional measurement techniques, making sure the equipment was on the right setting, performing correct unit conversion and calculations, and selecting appropriate data ranges for our best fit lines. These are all factors that could be corrected and refined if performing the experiment over again. So it goes without saying that one needs to save all collected data and record detailed procedural steps in order to be able to go back later and find the sources of error if necessary.